Natural convection-driven combustion is so 20th century by Noel Patonsu. The world has changed, technology has evolved, and we find ourselves at a crossroads. People have an inherent desire for the light and heat that a visible fire provides. Flames are a wonder in many minds and eyes. Even pets know that the best place to take a nap is near the fire. Having a good operating wood stove when the power goes out is a comforting experience. Nearly 2 million wood stoves and inserts were sold annually in the 1980s. Of course, wood stoves and inserts were sold before that time. They've been growing in popularity ever since. An estimated 11 million wood stoves are operating in the U.S. in 2021. Many people also use wood stoves across the world. Why people use wood stoves in the 21st century. People who live in a rural area where the electrical power is subject to power outages and prefer indoor environments near 74 degrees Fahrenheit are likely to think favorably of a wood stove. People who live in a region with cold weather may use a wood stove, and those living in an area of high-cost utility power may find that a wood stove reduces the electrical or heating fuel bill. Wood is also a carbon-neutral fuel when compared to other power sources, and that appeals to many people. What's more, wood stoves provide self-sufficiency, which is another reason people use them. Finally, a fire is considered a gathering place by many people. People simply like to stare into the flames of a fire. It is the best place to get warmed up. How wood stoves function. A wood stove is a sturdy metal masonry or stone enclosure where wood biomass is consumed by rapid oxidation in the form of fire. The resulting heat is dispersed into the house by radiant and convection heat transfer. The post-combustion gases are vented out a chimney by the buoyancy of the hot gases. This forces fresh combustion air into the wood stove. It's a simple system that works. Wood stoves work based on the buoyancy of hot gases rising and exiting the chimney, drawing new combustion air into the rapid oxidation exothermic chemical reaction zone of the fire. If we simplify a fire as a small campfire, the reaction zone is within the fire flames and below the fire, producing pyrolysis gases that are burned and visible by the flames. The buoyancy gases rise above the fire and creates a low pressure near the fire, and new, fresh, oxygen-rich air enters into the combustion reaction. It is a property of gravity, chemistry, and physics that's been used since the caveman days, and we still choose to use it today. There are 3 forms of heat transfer: conduction, radiation, and convection. In the campfire example, the conduction heat is transferred into the ground. The radiant heat goes into the knees, hands, and faces of the people facing the fire nearby. The convection heat is transferred to the air above the fire. Think of each form as 33% of the total heat produced by the fire. Put the fire in a wood stove, and the radiant and convection heat released by the fire are absorbed by the interior bricks and steel enclosure. Most of the conducted heat is transferred to the coals, ashes, and other fuel. Once the stove is at an operating temperature of 300 degrees Fahrenheit, heat radiates back onto the fuel enough to produce more pyrolysis gases and increase the heat release rate of the fuel while also increasing the chemical exothermic reaction rate. For each 18 degrees Fahrenheit, 10 degrees C, increase, the chemical reaction rate of a fire doubles. A wood stove operating at 250 will have a lower chemical reaction rate than the same wood stove operating at 350. The prior will consume fuel at a lower rate, and the latter will consume fuel at a higher rate, providing more heat to the living area. Controlling the operating temperature of wood stove will be the most influential parameter moving forward. Fire chemistry. We understand that fire combines high-temperature fuel pyrolysis products in an exothermic chemical oxidation reaction, resulting in heat and light. What is the chemistry involved? What goes in and what comes out? The chart below helps us answer these questions. Combustion air. Prior to 2021, very few wood stoves were monitored via data collection or electronically controlled. The power of the fire drives the natural convective draft and the entrainment of combustion air. The power of the fire can be derived and estimated by measuring the wood stove surface temperature and knowing the make and model of the wood stove. To keep the wood stove's exothermic reaction sustained, fresh combustion air is needed. A stock Lopi Revere wood stove consumes 10 to 50 cubic feet per minute while operating. This chimney was clean prior to these measurements. This air can be provided by an outside air kit or from interior room air. You can see in the table that higher operating temperatures have significantly higher airflow rates. These flow rates are with the control rod to the highest flow position. A combustion airflow rate of 42 CFM would support a fire power near 45 kilowatts. However, the manufacturer rates the stove at 20.5 kilowatts. Some residential structures have very tight construction with regards to air infiltration. There are often several motorized fans for clothes dryers, kitchens, and baths, moving air out of the house. Make-up fresh air is usually not managed in the home environment. The natural draft of the wood stove often competes with the motorized fans of the structure, working against the wood stove's draft. The wood stove operates on minimal pressure differentials, as small as 50 pascals. A fan in the house can pull the smoke and gases from the wood stove back into the living area. We don't want post-combustion gases in the living areas of our homes. In the future, the combustion air supply for a wood stove will be monitored for flow and pressure. The pressure of the combustion air system will be monitored to compensate for competing pressures within the living space. Consequences of uncontrolled combustion air. If combustion air is uncontrolled, safety, efficiency, and emissions all become concerns. I have been to many houses where the chimney got too hot and there were combustibles in contact with the chimney. Uncontrolled combustion air can lead to disaster. For example, a masonry chimney has stood for 100 years. Connect a wood stove without proper gaskets that allow combustion air to flow unregulated, and it turns into a fuel-limited fire, rather than a combustion air-controlled fire. Exhaust temperatures can exceed the masonry chimney's ability to absorb heat, and then it conducts it to the structural members that are in intimate contact. At some point, the wood structural members in contact with hot bricks start smoldering and release smoke. If it is noticed and addressed quickly, the damage can be limited. If the masonry chimney has an air gap to combustible material, the scenario is often avoided. It's interesting that the lack of a simple gasket can change the performance of a wood stove. Users often think that the wood stove works better due to the extra airflow. What they may not realize is there may be no method to reduce the airflow once the wood stove gets too hot. Combustion air control theory. All of this preamble was intended to bring everyone up to a point where we can discuss combustion air control theory. The fire triangle consists of three sides: fuel, heat, and oxygen. The combustion air contains the oxygen. Let's describe some scenarios and how we might plan for combustion air. Scenario 1. Let's start with a cold wood stove on a cold day. The operator arrives back home, sets kindling and wax fire starters with some paper, starts a fire, and moves on to other chores. A few minutes later, the operator needs to come back to the stove because smoke is pouring back into the room. Scenario 2. In this scenario, let's say it's cold outside and warm inside. The wood stove has been hot for the last 24 hours, and it had a refuel an hour ago. The room is 72 degrees Fahrenheit, and the stove is 350 degrees Fahrenheit. The smoke is at 10% opacity. The control strategy is to keep the stove temperature the same and reduce airflow slowly over the next hour and monitor sensors. Scenario 3. The wood stove was fueled 2 hours ago. the stove temperature is at 260 degrees Fahrenheit and dropping at 5 degrees per minute. The operator should refuel. If the operator does not refuel, then the airflow should be reduced as the temperature drops. Starting a fire in a wood stove requires a bit of preparation. Lighter starting materials, dry starting fuel, and then the larger sections of wood fuel. Starting a fire should be a simple and positive experience. You should be able to look back at the stove and see the fire grow into flames. Then you can check your email. Combustion air fans. A combustion air fan directly supplies fresh air to the wood stove for the purpose of combustion. It can draw air from outside the house or inside the room. The best combustion air fan is controllable for flow rate for a large range. The fan system should have a linear flow rate and predictable control system. Some manufacturers place the combustion air fan within the stove and preheat the air prior to pushing it into the combustion chamber. Natural gas and propane furnaces, industrial thermal oxidizers, pellet stoves, and boilers all use combustion air fans. They are normally single-speed fans that induce a draw for power combustion gases or inject combustion air into the reaction zone. They are specified by the flow rate and pressure needed at the operating range. These are normally single-speed blowers sized for the appliance. Not just any fan can be used as a combustion air fan. Fans are designed for pressure and flow rate. The same fan used for cooling a computer graphics card may not be usable for combustion control because of the pressure and flow rate may not be correct. The flow rate may need to be controlled over the range of the wood stove heating power range. If there's too much air, it's like blowing out a candle. The pyrolysis products will be moved out of the reaction zone and out the chimney, or an over-temperature event might occur. If there's too little air, the reaction will be reduced and the temperature reaction rate will diminish and smolder, producing more particulate matter. This is fire chemistry. Too much air may not be better, and too little air may not have the desired results. We are striving for stoichiometry, which is a perfect ratio. Combustion air fans for wood stoves. Now that I've explained the basics of combustion air fans, a new question arises. How would a combustion air fan for a wood stove be specified? This is a big question. There will be much debate on this, even if it is the proper thing to do to an existing wood stove. One method is to find the manufacturer's heat output of the wood stove. Here is an example for a wood stove with a heat output of 70,000 BTUs per hour. Initial calculations derive stoichiometric combustion airflow at 11.7 CFM. At this airflow rate, the heat output of the wood stove would not exceed 70,000 BTUs per hour. Any flow rate below 11.7 CFM would have a chemical exothermic reaction rate below this value. Testing would be needed to verify, but this is a good starting point. So will a wood stove with a fan that produces 11.7 CFM burn cleanly? Well, that's not quite that easy. Most fan specifications are at maximum flow without restriction. Once you place filter screens and plenum ducting to reroute the airflow rate is reduced. The airflow system needs to be calibrated. The fan needs to modulate over a wide range. How combustion air changes through the firebox. The air we breathe is 20.9% oxygen and 79% nitrogen, and the remainder is trace gases. Carbon dioxide is normally 0.4%, but can rise to 3% in a closed room occupied with people. Room air used for combustion air usually starts at 50 to 70 degrees Fahrenheit, enters the wood stove combustion air plenum, and is heated to higher temperatures and injected into the reaction zone. In the reaction zone, oxygen is reduced to the 12% range in an exothermic reaction that releases heat, water, CO2, and particulate matter. The post-combustion gases are now near 500 degrees Fahrenheit. They have also increased in volume and decreased in density. Passing by the secondary burner tubes or catalyst, the hot gases get another chance to react, consuming the last bit of particles and pyrolysis gases. As the molecules are heated, they get very active and bump into one another expanding the volume and increasing reactions as the gases near 500 degrees Fahrenheit. They have expanded 40%, accelerating these low-density gases up the flue. As long as oxygen is present in adequate amounts, further oxidation can still occur. As the active molecule gases, including water vapor, travel up the flue, any object below the dew point will form condensation out of the gases. The gases cool somewhat going up the flue. In seconds, the gases will exit the top of the chimney and rapidly cool from 400 degrees to 40 degrees. Water vapor will condense into clouds. The remaining smoke particles, soot, and unburned pyrolysis products will travel on and float in the air. These particles may be measured by PM 2.5 air quality monitors. Water vapor condensing in cold air above residence is common to natural gas, propane, pellet, and solid wood combustion devices. There are 5 wood stove operating phases. Starting. When a stove is starting, it needs a positive airflow that is proportional to the power of the fire. There should be no smoke backing into the living area. In addition, there's no need to open the wood stove door and let smoke out into the room. Warm up. This is when the stove is heating up to operating temperature. This should take 20 minutes. Heating or operating. Once the wood stove reaches operating temperature, watch the fuel status and room conditions. Manage the stove temperature into the Goldilocks zone, 250 to 425 F. Too hot and you use too much fuel, too cool and emissions increase. Not as much heat is produced and new fuel smolders. Turn on convection air fans to push heat out into the room. Refuel. This is the best time to add new fuel. New fuel takes time to heat up and off-gas, contributing to the fire. The stove temperature will diminish until fuel is heated to a level of pyrolysis off-gassing. There's also needs to be room in the firebox to place new fuel. Timing the refuel is not always a task that an average person can do efficiently. Cool down. This is when the fire runs out of fuel and only embers in the ashes are glowing. We don't want firebox post-combustion gases backflowing into the living area. There needs to be a positive flow out the chimney at a minimal flow rate for 48 to 72 hours. Why wood stoves don't come with combustion air fans from the factory? There have been models that did in the past. There are some wood burners now that do have a fan integrated into the design of the wood stove. The certification process for wood stoves is long and complicated. There are implied rules and concerns in modifying a factory unit. Then there is the maintenance of the moving components and cleaning filters. Compare this to a classic car. The manufacturer may not make the replacement parts that have worn out or broken. The owner may need to use third-party fabricated parts to repair it. The owner can add seat belts and better brakes to improve safety. The manufacturer may not approve of these upgrades, but the owner's insurance company may think differently. A safer vehicle is a lower risk. A safer wood stove is also a lower risk. Validating the method. Any new technology or new method to process material will need verification. Using the scientific method, we can develop new methods and processes. We will need to validate the method and document the process results. Emissions are measured by opacity at the exit of the chimney. Washington State allows 20% opacity. The chimney cannot exceed 20% opacity for 6 consecutive minutes of any hour. Many of the U.S. states are following this guidance. Any opacity monitoring device can be monitored. The signal from the opacity monitoring device can be recorded and integrated into a feedback control loop, adjusting airflow to the lowest opacity each minute of the day. The opacity monitor can be used to develop combustion air profiles for different wood stoves and wood fuel types. Solid wood burns differently than pellets or pressed sawdust logs. Softwood burns differently than hardwood. Components of a combustion air system. Combustion air systems include the following components. Fan or fans. These are motorized air movers. These will be centrifugal fans with a wide PWM control range. Plenum. Ducting from the fan to the wood stove adapter plate. This will be specific to each stove installation. The main component is 1-inch EMT along with 90s, Ys, and transitions to smaller and larger ports. Wood stove adapter. This is specific to each wood stove. This will normally be metal. Some high-temperature plastics and other materials are being evaluated. Fan controller. This will be a simple or complex electronic device consisting of firmware, temperature sensor, temperature, humidity, and gas sensors, and PWM control components. Each fan control channel has a PWM range of 0 to 100% at 12 volts DC. Few fans will run at less than 10%. A profile must consider this, as well as the fact that the fan has spin up and spin down times. The fan systems are sized for maximum heat output displayed on the placard or in the manufacturer's specifications. Here are some examples. Example 1. Lopi Revere, 70,000 BTU per hour, 20 kilowatts. Max fan flow is 10 CFM. Example 2. Anycubic Mini, 16,000 BTU per hour, 4.7 kilowatts. Max fan flow is 3 CFM. Example 3. Vogelzang TR007, 152,000 BTU per hour, 44.5 kilowatts. Max fan flow is 25 CFM. Fan pressure. Static pressure is the pressure that a fan can push prior to stalling at the airfoils. The amount of pressure adequate to push the cold column of air up and out the top of a chimney appears to be 100 pascals. Most axial fans can only produce 15 pascals, which is not sufficient. Summary. If we want to burn wood for residential heating into the 21st century, we will need to use our wood stoves safely, efficiently, and with minimal emissions. This can be accomplished using existing components and technology. Fire testing laboratories have been measuring smoke and oxygen consumption for decades. I know this because I've been maintaining and calibrating these systems since the 1980s. The cost of components is now a fraction of the early days. Microprocessors are a few dollars. Gas sensors are a few dollars. A wood stove retrofit package can be assembled for a few $100s. The system could notify the operator to contact a chimney sweep on a regular basis, determine that there is an obstruction, or discover that gaskets need service and request that service. A record can be kept for emissions and temperature with time and date references. Now, when a citation for emitting smoke is received, the operator may have the data to debate the matter. The existing wood stove installation will need to be evaluated. The chimney will need to be cleaned and inspected, the gaskets maintained, the fire bricks and secondary air delivery tubes inspected. This is work for chimney sweeps and wood stove technicians. Insurance companies may consider wood stove to be an increased risk. Using monitoring and controls, the wood stove may be considered safer than it once was. The records of operation and maintenance will be beneficial here. Wood stoves operate when the power goes out. Will these monitoring systems keep working? Yes. These systems use very little power, 5 watts, so a small battery can maintain the operation for more than 12 hours. A 12-volt supply can keep the system operational indefinitely. I have more than 5 years' experience developing combustion air fans for wood stoves. The benefits are steady performance, warm glowing coals, and clean glass, not to mention good consistent heat and reduced fuel loading. The room air has lower PM 2.5 levels. The cats sleep nearby, and my partner sits and reads a book by the fire. The kids will warm themselves and dry their outdoor clothing. The room doesn't get too hot, and we don't use more wood fuel than needed. Among the best information this paper has to offer is that any operating wood stove must be in good working order. Burning wood will build up deposits in the chimney system, and that needs to be addressed often. A missing or compromised gasket can result in structural damage or smoke and gases in the living area. A good inspection at install and scheduled routine maintenance are essential. Again, this is good, high-tech work for many people in the industry. All of this will be driven by science and data with the goal of warm homes and clean air for everyone. Thank you for listening.